Hi, and welcome to 5.2 Kinetic Friction and Internal Energy. In this lesson, students will be able to calculate the kinetic friction between two surfaces, and students will be able to describe what internal energy is and what causes it. So yesterday we talked about static friction. It's a force that resists the initiation of sliding motion between two surfaces that are in contact and at rest. They're stationary. Then we went through this. And friction always acts parallel to the surface of contact. So this is still true. Even for kinetic friction, it's still going to be parallel to the surface. And this was a little bit different. So for static friction, if you increase the applied force, then the static friction increases to meet it so that it stays at rest because it wants to resist the start of the motion. But that can only happen for so long. Then you reach the maximum static friction, and if you increase the applied force a little bit more than that maximum, then it starts sliding, and you don't have static friction anymore. It turns into kinetic friction. Kinetic friction is a force that opposes the movement of two surfaces that are in contact and sliding over each other. Okay, as long as the object is moving across the other object, it's kinetic friction. It doesn't matter if it's constant velocity or if it's accelerating, any type of movement, you're going to have kinetic friction. Sometimes it's known as sliding friction. So it says kinetic friction acts opposite the motion always. It's always opposing the motion. Friction always acts parallel to the surface, just like before. So you have your applied force here, and you have the frictional force here. And the object is moving, so there's some velocity to the right in the same direction as the applied force, and the frictional force is opposing that motion. When the applied force is equal to the kinetic friction, so these two vectors are equal to each other, then it moves with a constant velocity because the forces are balanced. And for today's lesson, we're going to stick with having the applied force being equal to the frictional force, and you're moving with a constant velocity. But then in the subsequent lessons, we'll increase the applied force. And what happens if the applied force is greater than the frictional force? What's going to happen there? So we'll see that. But for now, it's going to be forces are balanced and you're moving with a constant velocity. Just like that, moving with a constant velocity. The frictional force remains constant even if you increase the applied force. So for the static friction increased with the applied force until you reach the maximum. That's not happening with the kinetic friction. Kinetic friction remains the same. The only way to change the kinetic friction is if you change the materials, if you change the coefficient, or if you change the normal force somehow. But increasing the applied force does not affect the frictional force. It stays constant. So here are the two differences. This is just basically saying what we said before. As you increase the applied force for the static friction rises to meet it, and so that it stays in equilibrium and it's at rest. But this can only increase so much before it reaches its maximum static friction. If you increase above that, then it's going to start moving, and kinetic friction comes into play. And we're going to stick with a constant velocity where the applied force is equal to the kinetic friction. So the maximum static friction is always larger than the kinetic friction. Think about moving a table, right? So it says a block, you could do this with the table in front of you, but in this situation it says a block is initially at rest on a horizontal table. You push on the block with a slowly increasing applied force, starting at 0 newtons, then increasing to the maximum static friction. After you reach this maximum force, the blocks start moving. You continue to increase your applied force. Use this information to sketch a FF versus FA graph. So we are increasing the applied force after we start moving. And what I want you to do is, if you have a calculator that has like those little rubber pads on the bottom of it, that works well. Or if even the desk in front of you, slightly push on it until it just starts moving. Maybe you don't want to move your desk around, but if you have something that on your table that you can kind of push on until it reaches the maximum static friction and then push forward, what do you notice about the force it takes to start moving the object and the force that it takes to keep the object moving? Maybe you've noticed this if you are moving furniture across the floor. You have to give it a little bit of a push to get it going, and then once it's going, it's easier to keep that object in motion. And that's because the maximum static friction is larger than the kinetic friction. It's easier to move the object because the kinetic friction is less than that maximum static friction that's holding the object in place. So anyway, what do you think a graph of this might look like? You could pause the video and try to sketch out a graph of a FF versus FA graph. So the FF versus FA graph would look like this. You're increasing your force of friction starting at 0. You're increasing your applied force, and what happens to the force of friction? Okay. It actually looks something like this. So here's your applied force in newtons, and here's the friction resistance. And this is both static and kinetic. So you have 0 applied force, and there's no frictional force. But as you increase your applied force, now you're at 20 newtons. The static friction is also 20 newtons because you're in equilibrium. You're still at rest. Then you increase your applied force enough so that you have 50 newtons. That's the maximum static friction. And this is what's called the threshold of motion. So if you increase your applied force past that 50 newtons, it's going to start moving. And the static coefficient turns into the kinetic coefficient. Now, the kinetic coefficient is always less than the maximum static coefficient. Actually, just the static coefficient. So since the kinetic friction is less, it drops down really quickly. And even if you increase your applied force, now it's 60 newtons, now it's 70, now it's 80 newtons. My applied force, I'm pushing on it harder, but the kinetic friction stays the same. So this is just showing in a graph what we talked about in that kinetic friction slide, that the kinetic friction stays at 40 newtons in this case. And even if you increase your applied force, all right, the kinetic friction doesn't change. It's not like static friction where the static friction is meeting your applied force every time until you reach that maximum static friction and you start moving. So that's the difference between static and kinetic. Just remember that the kinetic is always less than the static coefficient. Let's do a quick example here. It's very similar to yesterday's, but instead of 5 kilograms, it's 10 kilograms. And part A says, well, it's a 10 kilogram wooden block on a wooden table. So that tells you something right there. And part A says how much force is required to start the block moving. So right now it's at rest. How much force do we need to exert to move it? So this is going to be static. And then how much force is required to keep the block moving at a constant velocity. All right. So if it's moving, then that's going to be kinetic. So let's start by making, for part A free body diagram. You're going to draw the block. You have your weight, Fg, you have your normal force. Those two are equal to each other in this case. And we're going to increase our applied force until we reach the maximum static friction. What is that maximum static friction? That'll tell us how much applied force we need, which is technically what they're asking for in part A. How much force is required to start it moving? That they're saying, what is the applied force that you need? So then we could write our given information. The mass is 10 kilograms. We're on Earth. And it's wood on wood, and it's static. So you look in the front of your reference table, and the static coefficient, what is it? Take a look. Did you pick out the right one? The static coefficient for wood on wood is 0.42, just like yesterday, okay? And then you could piecemeal it if you want. You could do Fg, I would probably do Fg equals mg. Plug in your numbers, and you get a weight of force due to gravity of negative 98 newtons. So that goes right here. Our free body diagram tells us that they're going to be equal because these are the only two forces in the y direction, and you're not going through the table or up the table, so those forces must be balanced. All right, so now you know the normal force, and you can calculate the frictional force. So you do Ff equals mu Fn. Static, so FFS is equal to 0.42 times our normal force, 98 newtons. So the static friction, this is really the maximum static friction, is equal to 41.16. I'll leave it a long decimal because we're going to compare it to the kinetic. Really 41.2 is fine, or just even 41 newtons. That's the maximum static friction that we need to overcome. So if you apply a force of 41.16, just a little bit more than that, you'll start moving. Okay, so new stuff, that's review. New stuff for today is what happens if it's moving. All right, the weight is the same, the normal force is the same, but instead of FFS max, all right, we want to know what is the force of kinetic friction so that we can apply the same exact force of kinetic friction so that it's moving at a constant velocity. We want our applied force to balance out that kinetic frictional force. So now we pull out another piece of information from our reference table. We need to know the kinetic coefficient of friction. And the kinetic coefficient between wood and wood is 0.30. This still holds true, so we could keep that there. We're just doing another friction formula. Ff equals mu Fn, but we're doing kinetic now. So the force of kinetic friction is equal to 0.30 times our normal force, which is still 98 newtons. And the kinetic friction between those two surfaces is equal to only 29.4 newtons. So the kinetic friction is equal to 29.4 newtons. And if you applied 29.4 newtons here, then those two forces would balance each other out. You would not be accelerating. You would move at a constant velocity if you completely matched your coefficient of friction. And let's compare them. So which one is larger? The maximum static friction is always larger than the kinetic friction. And you could even compare really quickly by looking at your reference table. If you compare the static and the kinetic for each of those situations, which coefficient is always larger? The static coefficient is always larger than the kinetic. So therefore you'll have a larger static friction force. Okay. Oh, and then here's a little animation. Beautiful. Look at that constant velocity. The next lesson will accelerate, and then the lesson after that will decelerate. So one more example here. It says you're pushing on a 20 kilogram crate across a horizontal floor. You push with a force of 80 newtons so that the crate moves with a constant velocity. This is important. The material of the crate and the floor are unknown. Is the frictional force static or kinetic? What is the frictional force acting on the crate? And what is the coefficient of kinetic friction between the crate and the floor? So what do you think? Is the force static or kinetic? Well, if you're moving it across the floor, if there's any kind of velocity, then it's going to be kinetic friction. So it's kinetic friction. And let's calculate what the frictional force is. Let's start by drawing a free body diagram. So we have our block. We know that there's a weight and it's on a surface, so we know there's a normal force. And we know they tell you your applied force is equal to 80 newtons. And we just said, okay, there's some kind of frictional force there, FFK, okay? The given information, mass is equal to 20 kilograms, G is equal to negative 9.8 meters per second squared, and that's it. They don't tell you what the material is, so you can't find the coefficient. So it says, what is the frictional force acting on the crate? And here is something that people might try to do. They might try to go, right, okay, frictional force. I know there's a formula for friction. And they might even say, okay, I could figure out what Fn is because I know the mass. So let me do my Fg equals mg equation. And I know that this is 196 and the forces are balancing each other out. So the normal force is 196. And okay, so the normal force I know is 196. So let me write that over here if my pen lets me. 196. Oh, but I don't know the coefficient. Oh, and they're asking for the frictional force. So there's two unknowns, and I can't use this to find the frictional force. So what the heck do I do? You have to look at what the problem's telling you. You're pushing with 80 newtons, and the object is moving with a constant velocity. Just like before, if these two forces are balancing each other out, it's technically at rest in the y direction. It's not moving anywhere in the y direction. It has a constant velocity of 0. And in the x direction, these two forces must also be balancing each other out because you're moving with a constant velocity. All right, you're not accelerating. So we know right away, without having to do any work, that this is equal to 80 newtons. It's matching your applied force because the forces are balanced. If you wanted to write an equation, you could say, okay, the net force in the x direction is equal to Fa plus FFK. And since it's moving at a constant velocity, I know that the net force must be equal to 0. There's no unbalanced force acting on this thing. The applied force is 80 newtons, and the frictional force, plus FFK. All right. We don't know what that is, but when you solve, FFK is equal to negative 80 newtons because it's pointing to the left in the opposite direction. But you don't have to carry this negative over here because you just don't need to, okay? So the frictional force is equal to 80 newtons. That's kind of the trick with this one. If they're telling you it's a constant velocity and they tell you what the applied force is, then they're telling you what the frictional force is in this situation when it's like this, okay? So the coefficient of kinetic friction, you just take your frictional force and divide it by your normal force, which we found before, and you get about 0.41, 0.408. And there's no units on that because this is a Newton divided by a Newton. Okay, so the frictional force they told you in the problem, you just had to be, look at your free body diagram, and the coefficient we said was 0.41. Cool, so that's a little bit tricky. And then I also like to do this internal energy demonstration. So what I want you to do, and come on, try it at home. You can do it. Put your two hands together and rub your hands together like you're trying to warm them up. What's happening is there's friction between your two hands. And what does friction cause? Keep rubbing your hands together as hard as you can, as fast as you can. Keep rubbing your hands together. Do you feel that? Do you feel the warmth? Come on, keep doing it. Keep rubbing your hands together. Very hard, very fast, rubbing your hands together. What are you doing? You're using friction to cause internal energy or heat. And that's what happens when you rub two sticks together. You get fire. Yeah, so friction causes internal energy or heat. Now, in Unit 8, we talk more about energy. But for right now, there might be some multiple choice questions saying something about internal energy and how friction causes internal energy or heat. All right, so that's kind of fun. And then since you just rubbed your hands together, I always kind of show this video in the classroom. It's from Karate Kid, the original one, and Mr. Miyagi rubs his hands together to help heal, magically heal. I guess his name is Danny. I forget what the character's name is. Daniel's son, right? And, so there's a video clip of him rubbing his hands together. But in that clip, it's the whole scene with like, oh, paint the fence and, wax on, wax off. And Danny doesn't know why he's doing all these chores. He's trying to learn karate, but Mr. Miyagi has him do all these menial chores and he doesn't understand why until this like kind of cool scene where it's like, oh, I understand why you made me do all those mundane things, painting the fence, waxing the floor. And then I like to do Mr. Miyagi says versus Mr. Nangle says. So Mr. Miyagi says, sand the floor. And I say, do your assignments. Mr. Miyagi says, wax on, wax off. I say, study for tests and quizzes. Mr. Miyagi says, paint the fence. I say, come to class on time. Mr. Miyagi says, paint the house. I say, meet your deadlines. Why are we doing all these mundane things? Do you know why? Doing these things will help you after you graduate. Yes. You will have many new responsibilities. Nobody is going to do the work for you. Learning to be diligent and think critically are skills that you will actually use in your life, even if you don't ever have to calculate the coefficient of friction between two surfaces. So I get it all the time. Mr. Nangle, when am I going to actually have to use this stuff in real life? You might not have to break out your calculator and calculate the force of friction or anything like that, or the acceleration due to gravity, you know. But it's more about learning how to think critically and be diligent in your studies and in your work and building good habits, because nobody's going to do the work for you. You have to do it yourself. So it's all about building good habits. And you better learn now before you hit the real world, and then you have to learn as you go. It makes it that much more difficult. So get into good habits now and learn how to work hard, so that your life is easier later. And that's about it. Thanks for watching and have a great day.